Copper is one of the most widely used metals on Earth, and the very first metal humanity ever learned to master. Its story runs side by side with the rise of civilization itself, going back roughly 5,000 years before Christ, when it was first hammered into tools, weapons, and everyday objects. Today, about 25 million tons of copper are produced worldwide every single year. But have you ever stopped to ask where copper actually comes from, and how we pull it out of the ground? Today we're following every single step of that remarkable journey, from mining and extraction, through refining, all the way to the moment copper becomes the essential components that keep modern industry running. Stick with me to the end, because what you're about to see will change the way you look at this metal that's hiding in absolutely everything around you, right here on Stories Behind Everything. The metal that powers modern civilization. Modern civilization simply wouldn't function without copper. This metal shows up in nearly every corner of our daily lives. Motors, heating systems, the electrical cables feeding power to entire cities. Copper is one of the finest conductors of electricity and heat science has ever identified. It also carries high corrosion resistance, and it's extraordinarily flexible and malleable, able to be drawn into wires, rolled into sheets, and formed into highly complex components. And here's the most impressive part. Copper can be recycled endlessly without losing a single one of its properties, which makes it one of the most strategically important metals both for industry and for the long-term sustainability of our planet. Prospecting, drilling, and blasting copper is scattered across the Earth's surface, mostly inside sedimentary rock formations. Getting it out is a complex, multi-stage operation. It all starts with pinpointing areas that show promise for copper ore deposits. Specialized teams run detailed geological surveys, analyze soil samples, and apply advanced prospecting techniques to find regions where copper sits in concentrations rich enough to make mining economically worthwhile. Once a deposit is confirmed, drilling begins to pull more detailed samples. Heavy-duty equipment bores strategic holes into the rock mass, known as blast holes, following patterns laid out with precision by mining engineers. Industrial explosives are then loaded into those holes. The types vary depending on the geological character of the site, but they're generally nitrate-based compounds developed specifically for mining work. After the charges go in, the holes are packed with an inert material called stemming. That's what contains the explosion, driving its energy straight into the rock and delivering a more efficient, more controlled fragmentation. The detonation is fired in a rigorously planned sequence that accounts for safety, energy efficiency, vibration control, and the ideal size of the fragments left behind. This controlled blast shatters the rock into smaller pieces, making it far easier to load, transport, and process the ore in the stages that follow. Loading and hauling the ore. The shattered rock is loaded onto off-highway haul trucks, enormous machines built to work under extreme conditions, capable of carrying more than 440 tons of material in a single trip. On average, it takes roughly 200 tons of rock to yield just 1 ton of copper, about 11 to 13 pounds of copper per ton of material extracted. Loading is handled by massive hydraulic excavators that scoop up the shattered rock and drop it straight into the truck beds. Once they're loaded, the trucks climb the spiral ramps carved into the mine walls, ramps engineered specifically to carry that colossal weight. Rock fragments carrying too little copper to justify the cost of processing get pulled aside and sent to waste areas known as waste rock dumps. But anything with an economically viable copper content above 0.3% moves on to beneficiation, where it's prepared for the processes that will pry the copper away from the surrounding rock. Beneficiation starts with crushing. Huge blocks of rock are broken down into smaller fragments by industrial-scale crushers. The crushed material then rides conveyor belts to the processing plant, where it's ground down inside massive industrial mills loaded with iron balls that pulverize the rock into extremely fine particles. At this stage, the ore is mixed with water to form a slurry, which makes it far easier to move and to control particle size. This step is critical because it frees the copper minerals from the rock matrix they were locked into. After grinding, the ore heads to concentration, where the copper is finally separated from the other minerals through a process called flotation. Specific chemical reagents are added to the slurry to make the copper particles hydrophobic, so they cling to air bubbles pumped into the tanks. Those particles rise to the surface and form a copper-rich froth that's skimmed off and collected. The result is a copper concentrate with far more metal in it than the original ore, but it still carries impurities and it still needs refining. That final extraction happens mainly through two methods: smelting, which uses extreme heat to separate the metal, and leaching, which dissolves the copper with chemical solutions before the final refining. In leaching, the ore is stacked in heaps or loaded into tanks and treated with an acidic solution that dissolves the copper locked in the rock. The dissolved copper is then separated from the solution and recovered through purification stages, yielding high-purity copper ready for industrial use. In smelting, the copper concentrate is fed into industrial furnaces and heated until it melts. As it heats, the copper separates from the impurities, which combine into a slag that floats on top of the molten metal and gets skimmed away. The resulting liquid copper, known as blister copper, around 98% to 99% pure, is poured into molds to form thick metal slabs called anodes, each weighing roughly 500 pounds. Those anodes then move on to electrorefining. Here, the copper anodes are submerged in an electrolytic solution and hit with an electrical current. The copper slowly dissolves and redeposits onto other plates, building up a fresh layer of metal with a purity above 99.9%, ready for electrical wiring, electronic components, and a vast range of industrial products. When those high-purity copper plates arrive at manufacturing facilities, they're heated in industrial furnaces until they turn back into liquid metal. That molten copper is fed into continuous casting systems, where it's shaped into bars, billets, or rods that become the raw material for countless applications, from electrical wiring and tubing all the way to precision-engineered components for practically every sector of modern industry. Thanks for watching. Got an idea for what we should cover next? Drop it in the comments below. And don't forget to hit like, subscribe, and stick around for more of the stories behind everything.